Well, this is a model of the first television transmitter tower in the world, erected here at Alexandra Palace in 1935. It was built to support a small load, just an aerial, but it's extensively braced in order to withstand strong wind loads from any direction. And this new version of one of the towers which carry the high voltage electricity cables of the national grid was designed in 1979. In this case, the loading may be quite large, particularly when the cables are weighed down with ice or snow or are pushed to one side by strong wind loads. And again, the structure must be capable of withstanding these loads by being adequately braced. And this is a section model of one of the towers of the Severn Suspension Bridge. And in this picture, you can see that the road is supported by long cables stretched between the two tall vertical towers on either side of the Severn River. And we can use this model to illustrate some of the main structural features. The massive towers have to support the weight of the bridge, and so they're in compression. And if we look at the forces acting on the top of one of the towers, we can see that the cables themselves must be in tension, as we would expect. Now, in this program, we're not going to tell you how to design a bridge, or any other structure for that matter, but we are going to be looking at the principal components of all structures. So, what are these components?
Well, by components, we don't mean nuts and bolts. When an engineer is designing a structure, he's trying to find a good way to resist the forces that act on it. He has to consider the possible ways in which the members of the structure might fail to do their job. That depends on how the forces act on the members. So, a classification of the members, according to the forces on them, is very useful for the designer. That's what I mean by different structural components. So, I'll explain briefly these components to you, and then I'd like you to look out for them in the structures that you'll be seeing during the rest of the program. If the forces put the component into simple tension, then it is called a tie. The result of tension is elongation. If the tie stretches an unacceptable amount, like rubber would, then it is not stiff enough, and it is said to have suffered a stiffness failure. If it actually breaks in two, then it wasn't strong enough. This is a strength failure. So, for a tie, there are two possible sorts of failure: strength and stiffness. If the forces put the component into compression, it is called a strut or column. A strut can fail in strength or stiffness, just like a tie, but there is also another way: it can buckle. This is an example of a stability failure. When the forces are applied perpendicularly to the component, it is called a beam. The shape change of the beam is mainly due to bending. This bending corresponds to tension on one side and compression on the other. The beam is also in shear. Using this large element gives an idea of the shape changes in the components. But normally we want to look at the stress and strain at one point of the material, and for this we need a very small element. The load on the beam will cause shear stresses on the element, but this would make the element rotate. Actually, the element is in equilibrium, so there must be shear forces on the other faces too. They must have the same magnitude and be in this direction. These are the complementary shear stresses. Of course, these stresses must cause a shear strain. If we move our viewpoint by 45 degrees, then the same stress and strain looks like this. This is the same as a tension in this direction. This would be a normal stress on the faces of this element. So we see either normal stresses or shear stresses at this point, depending on the element that we choose, or different combinations of stresses at different angles. Even for more complicated stress fields, there is always an orientation of the element which has zero shear stress. The normal stresses are then called the principal stresses. Usually there are principal stresses on all the faces. There is another orientation at which the shear stresses are at a maximum. Whether the material will fail or not generally depends upon the principal stresses and the maximum shear stresses, and it's Moore's circle that we use to determine them. In summary then, there are three sorts of failure, the three S's: strength, stiffness, and stability. A tie is a member in tension, and the design of a tie is nearly always limited by strength. A beam is a member in bending. The design of a beam is nearly always limited by stiffness. And a strut or column is a member in compression, and the design of a column is nearly always limited by stability. It would be very hard for me to break this piece of wood in straight tension. But in bending, well, that's easy. And in compression, it's easy too. So it's very important for the designer to know exactly how the forces are being applied to each of his members, for him to design each member accordingly. So look out for the different structural components in the structures that you'll be seeing during the rest of the program.
Well, we're going to demonstrate the design of compression components with these studio structures. Each structure is designed to carry a simple load from here. And if we do a static analysis about this point, we'll find that these tie wires are in tension, whereas this strut is in compression. And with this particular geometric arrangement, the compression force in the strut is about twice the applied load. Well, the structures differ in one important respect, and that is in the construction of the compression member. In this first structure, the strut has a solid cross-section, whereas in the second structure, with an exactly similar geometric arrangement, the strut has a hollow cross-section. And we'd expect this strut to have a larger resistance to buckling than the first one, even though it's made of the same amount of material. In fact, both struts have a mass of 15 grams, or about half an ounce, as does the third one.
Yes, but on this one the material is even more spread out. It's called a space frame. The compression force is carried in these four corner longerons. They comprise about 40% of the mass of the strut. But because they're separated, they could buckle independently. And therefore, we have to have all the bracing to make them act in unison. And the bracing is about 60% of the mass. We'd expect this one to perform even better, but it's at the expense of much more complicated construction.
Well, we're going to test these structures to destruction by slowly increasing the applied load on them. And as we do so, try to anticipate how the failure might occur. Now, there's a ½ kilogram load on them at the start, so they're already carrying about 30 times their own mass. Right. I'll start off by adding a ½ kilogram, making a total of 1 kilogram on structure number 1. No, it's not going to take it, even at this load. As you can see, the strut is buckling. If I decrease the load, it straightens out. It's stable. But as the load increases, it's unstable. Moreover, once it starts buckling, it's no longer just in compression, it's also in bending. And the maximum bending occurs about the middle. So if I release the load, it breaks in bending. But remember, it started off by failing in compression, a stability failure. Let's see if number 2 can do any better. Right, ½ kilogram on, making a total of 1 kilogram on structure number 2. Yes.
Right, we'll go for 1 kilogram on number 3. Yes, that seems okay.
1½ kilograms. Okay.
Right, going for 1½ on mine. Okay.
2 kilograms. still holding.
Two kilograms going on. Okay.
2.5 kilograms. Fine.
2.5 going on. Yes, that's okay.
3 kilograms.
That's 3 on mine. Yep.
And they're both holding at that loading, and that means that they're actually carrying about 200 times their own mass. So we'll try 3.5 kilograms. Okay?
And a half on. That's
4 kilograms. It can't take it. Just as in the first case, it's starting to buckle and bend. If I reduce the load, it's stable. Increasing the load becomes unstable. And with the load released, it breaks. Again, it failed from a buckling failure, but in this case, it had 1, 2, 3, 4 kilogram loading, a lot higher than the first one. So it looks like this box section really worked. Well, John, can you do any better?
Well, let's see if mine can actually survive with 4 kilograms on then. Going on. It's 4 kilograms on. Yes, it's okay.
Okay, you win. Well, these are basically simple structures carrying a simple load, but engineers have to deal with much more complicated loadings than that. Well, a good example of a real engineering structure is the National Grid Tower. So we asked the structural designer of the tower to explain some of the features involved in the design.
As a starting point in the design of a new transmission tower, I look at the job specification. That is, what the tower has to do from a structural point of view. This model indicates a typical transmission tower. The height is 46 meters, and it has to support conductors at the peak and each of the cross arms. The span of the conductors is 400 meters, and at this model scale means that the next tower will be in the next office. The reason for the design of a new transmission tower is the development of a new conductor made entirely of aluminium alloy. This is the length of this conductor, and if we look at the ends, we can see that it is made up of a number of smaller wires, 61 to be exact. The conductor is lighter, but larger in diameter than the previous steel-reinforced conductor, which has been in use up to now. Let us have a closer look at this tower. A transmission tower is basically a pin-jointed cantilever whose height is determined by electrical clearances from the lower conductor to ground and from conductor to conductor to prevent sparking between them. It has to carry vertical loads from conductors and ice and horizontal loads from wind on the conductors and steelwork. If we have a look at this diagram, 3 typical design cases are shown. Case 1 is for a very high wind of 110 miles per hour blowing on the conductors and tower. Case 2 is for heavy ice deposits on the conductors with a moderate wind blowing. And case 3 indicates the loading on the tower if one of the conductors breaks. The weight of the tower itself is 15.8 tons. And if we now have a look at this high wind case, we see that the weight of the conductors is 282 kilonewton. The horizontal load from the wind blowing on the conductor, 316 kilonewton. And the wind on the tower itself, 225 kilonewton. If we now go to the second case, for wind and ice, we see that the vertical loading has increased considerably to 1,046 kilonewton. but the horizontal loading is now slightly less than it was before. Case 3 indicates the loadings on the broken conductor. And you can see that this loading of 151 kilonewton, acting at the end of the crossarm, imparts a very heavy torque to the tower. Other loading conditions are possible and must be taken into account, but these three are generally the worst. The effect of these loads on the tower can be seen on the next sketch. With the wind blowing from left to right, the whole leeward side of the tower is in compression, and all the bracing members leading to this, whereas the windward side of the tower is in tension. Similarly, half of the bracings are in tension. The vertical loading on the crossarms produces compression in the lower chords and tension in the upper chords. The load in each leg at the base is normally only about 100 kilonewtons, but this increases to 1200 kilonewtons for the design case including ice and wind. In order to support this heavy compression, the leg has to resist buckling and must be supported at frequent intervals by bracing, which can be seen on the next sketch. Various types of bracing are possible, and the choice depends largely on the width of tower at the position where the bracing is required. The width of tower obviously determines the loads in the members, and various trial designs have to be made before deciding on the most economical width of tower. 3 different types of bracing are used in this tower. Ordinary cross bracing, acting in tension and in compression, where the 2 members are tied together at the center. The second type is very similar to the first type, except that there are secondary members inserted, which help to brace the leg and also prevent the bracing from twisting. This improves the strength of the bracing. The third type is K-bracing. This is used where the width of tower is too wide to use either of the first 2 types. Because the wind is reversible, all tension members must be designed for compression when the wind load is reversed. Once the worst loads have been determined, the size and shape of members is decided. The usual type of member used is a high tensile steel angle, similar to this one, but of different sizes. Although the model is too small to show it, all connections are made of high tensile steel bolts. This enables the tower to be fabricated in small pieces and erected using the minimum of equipment. This is an important point when one considers the difficulty of access to some of these tower sites. When the design of all the members has been completed, and remember there are nearly 600 loaded members in this tower, the design is checked using a computer for all possible loading cases. This is a typical output from our computer for this particular tower, and you can see the amount of calculation it represents. Although the design of the tower is carried out theoretically and checked with the aid of a computer, it is necessary to carry out a full-size tower test to convince people that the tower will withstand the specified loads, and also to improve our knowledge of the behavior of towers for the design of future towers for maximum economy. The requirement for maximum economy is obvious when one considers that thousands of these towers could be required. Tests on transmission towers for use at home and abroad are carried out at the CGB Tower Testing Centre at Jeddah, where the specified loads are applied by huge rams pulling on steel wire ropes attached to the structure.
Now starting up the correction to load point 4 transverse.
7 tests were carried out on this tower, all of which were successfully taken to 100% of the design loading and held for 1 minute without failure.
That's the 1 minute hold period elapsed at 100% working load.
Loading on now to failure. These remain well cleared.
105%.
The final test, simulating the effect of a broken conductor at the middle crossarm level, puts maximum torque on the tower.
110%.
And this test was carried out until failure occurred. Load cells were showing the actual loads being applied, and all the highly stressed bars in the tower were being monitored by strain gauges, which indicated that the critical bars in this test were the cross bracings under the middle cross arm.
125%. 130%.
133% of working load. 137%.
140. Stand well clear everywhere.
141. It's getting close.
142. 144.
There she goes.
Suddenly, one failed in compression, then the other failed in tension at the bolts, exactly as expected. The actual strength of the tower required was 130% of working load. I predicted that collapse would occur at 140, and the tower actually failed at 3% more than this, probably because the steel quality was slightly better than that assumed in the design. As far as I'm concerned, as a designer, that failure was a success.
Well, that structure easily took its design load. So finally, let's just see how much better John's third structure is than the other two. Remember, the first two broke at 1 kilogram and at 4 kilograms.
16. And a half. 17 going on. I don't think I can get any more on. Try one more. Go for 18. Well, that's 18 on. I just can't get any more on. No, it's coming over. No, the weights are actually going to fall off. The hanger just isn't long enough. Well, that's 18 kilograms on. Ratio well over 1,000. Actually, about a ratio of about 1,200 to 1. So I think that makes the point fairly well that the design of the compression member is very critical.